This is another Huffman code question. This is a past paper question. So we've got a Huffman tree that they've partially filled in the numbers for us, so we know which side to go. So we've got 0 and 1. So that means 0 and 1 goes on all of these branches. So we can fill that in. Even if we don't need all of them in the end, we might as well fill the whole thing in so we know where we're at. So all we're doing is generating the idea of how the code works. And then the first question down here is use the Huffman tree in figure 1 to state the Huffman encoding for the string most. So we need to find M. M is here, so we've got 1, 0, 1, 1, 1. I'll just double check we wrote that down correctly. 1, 0, 1, 1, 1 for M. And then O is next door, so it's 1, 0, 1, 1, 0. So we just went down here 1, 0, 1, 1, 1, and 1, 0 in that case. So then S. So S is up here. So that is 0, 1, 0. And then finally we've got T. And T is over here on this side. We've got 1, 1, 1 for T. So we did that and we got all 3 points for that. So all you have to do in this is make sure that you take note of which ones they've filled in for you. Either that or they might give you the path to a particular letter. And if they've done that, then you can work out the zeros and ones from that. And that's the way to do that one. So then we've got a part B question, which is not really necessarily to do with this tree. It's just general about trees. So it says that a student was asked to describe how Huffman trees could be created for this string in figure 2. So the string being, we didn't even look at the string in figure 2. The string was computer science is the best subject. It's not particularly original, but there it is. So the student response is I would count the number of times each character appears in the string and create a frequency table sorted alphabetically. Well, I think that's the first mistake there, because we don't want to sort it alphabetically. We'd like to really sort that by frequency. So the first one we should say is not sorted alphabetically, but sorted in order of frequency. And that's definitely the first mistake that's been made. So then, for example, the letter S has the highest frequency in figure 2. So let's just check that out to see whether it does or not, because we've sort of moved it over. So the letter S, does that have the highest frequency? Well, there's 1, 2, 3 of them, 3 S's, or is there 4? 1, 2, 3, there's actually 4 S's. So there's quite a few of them, but does that have the highest frequency? Well, there were 6 E's, so it doesn't have the highest frequency. So we could say that as another issue. So we could say letter S does not have highest frequency. Letter E does. Okay, so next I would take the two characters with the highest frequencies and combine them to make a new node. Well, we don't want to do that. We don't do that in Huffman. We start with the lowest frequencies, not the highest. So we could say combine lowest frequency, not the highest. And then what else do we say? It says the new node would be added to the end of the frequency table. It's not added to the end of the table, it's just added in the right place, in the place it should be. So new node not added to end, but inserted in the correct place. Based on its combined frequencies. So we've got all 4 points on that one now. So let's assume that the rest of it that they've talked about is correct. So the two characters with the lowest remaining frequencies are combined. Well, yeah, that's true. The process is repeated until all characters have been added. Yeah, so that's pretty much the case as to how that works. So we've got those 4 reasons there. That's a tricky question. It needs you to think about what's been written and know how to do a Huffman tree. So I'm sure we've definitely made some Huffman trees in the past, but you just need to remember how to make them for that. So then the last part on this is a calculation. So they've done half of the calculation for us. They've actually done the longer bit that we might have to calculate. So when the Huffman tree is used to the string in figure 2 can be represented using 130 bits, it says. So they're telling us it's a 36 character string. It could be encoded using Ascii. So we need to remember that Ascii is a 7-bit code. So that means there's 7 bits for each character. So we could work out 36 times 7, which is 252, I think. That would be bits. But then to work out the saving, we need to take away the 130. So we end up with 122 bits for that one. So that's all the points for that particular Huffman coding question. We looked at the tree, we added the numbers to it, we then worked out what the value of the code would be for most here, M-O-S-T. We then came up with 4 mistakes that had been made in the construction of the tree, and we've worked out the saving that the tree would make for the figure 2 computer science is the best sentence, and that was 122 bits.